So we have a space-time which is x1 independent, right? So in general, what it implies is that we have conservation of momentum, and that's the argument for why we have conservation of momentum. Now you can consider a test particle that moves in this space-time, and you can ask what is the conserved quantity for the motion of this particle in this space-time. That would be the momentum of the particle. Now, if you take the stress energy tensor of the particle and plug it in this expression, you will recover the momentum of that single particle. These are just different. This is a general way of finding for arbitrary matter fields that exist in this space, and this is the general expression for the conserved quantity. Once I specify what is the matter field, for instance, I say I have a single particle that is moving. Then for any specific case, you can actually derive that constant of motion. So these two things are related to each other. One is the general case, one is the specific case.
So you were asking, like, using the stress energy tensor of a point particle, finding that you get exactly the same.
No, this is if you write this, that is fine. That would be the legitimate solution to the problem. You didn't have to
for any particle,
for a point particle, not for a field. For a point particle, this is the equations of motion for a point particle. And you can easily derive that for a point particle, this quantity is constant along the motion. You can also go through this step and check it that if you plug in the stress energy tensor for the point particle, you will recover.
Okay. Yeah.
So is the logic clear now?
Yes. Okay.
Other questions? Okay, I'm supposed to lecture now. So let's see if I can finish by 3:30, then we can do some other problems afterwards. Otherwise, we can do them on Friday. Oh yeah, please give me your homework if you have. Okay, so yes, lastly we talked about manifolds. The tangent space, we talked about curves and vectors which are tangent to the curves. And we talked about metric that allows us to calculate the distances and angles between vectors. Today we want to talk about curvature. But let's start from some easier operations that we would like to do on manifold. So we said that in general we have one tangent space at every point on the manifold. So if I consider two vectors V1 living here and or V living here and W there, it doesn't. It's meaningless to compare these two together because these are living in two different spaces, two different linear spaces. So if we want to compare them, we have to somehow transport them, one of them at least, to the other point, so that we introduce another vector V tilde that lives in this in the tangent space of this other point. So let's say this is a point. This is point P, and this is point Q. And we want to define a V tilde that lives in the tangent space of point Q and somehow related to V. That requires some protocol, some instructions to define this new vector. So a priori, it's not obvious how to do that. And that protocol is called parallel transportation. So we want one way of doing it. So if I take this, if I choose some coordinate system, and let's say P and Q points are infinitesimally separated. So this is like x plus dx. So if we take this to be the same vector in this coordinate system, that is not a good, that's not a very satisfactory protocol because it's very coordinate dependent. So if I do it in different coordinate system, I'm going to get different answers. So what we do is that we add to this another piece that is going to cancel this coordinate dependence. And this another piece is exactly defining our protocol for doing the parallel transportation. Now, we want this V tilde mu to be a vector in the new point. So on the coordinate transformation, it has some definite transformation property. We know that V is not a vector in this new point. So this gamma itself is also not a vector. But it's exactly not, its transformation differs from that of, it's not a tensor, but its transformation differs from that of a tensor exactly in such a way that it cancels the mismatch of V mu. Okay, another thing to keep in mind is that if I can have the choice of this parallel transportation is not unique at all. So if I can have two different ways of defining parallel transport, so V and V prime, V tilde prime, that is defined by another gamma prime mu alpha beta dx alpha v beta. And then if I take the difference of the two, then the difference has to be a vector, sorry, a tensor. So if I can say the difference, that is C mu alpha beta, and this is a rank 1-2 tensor. Because if I take the difference of these two equations, the V's cancel. So I get the difference of these two, and then I have objects which are, I'm dealing with I'm dealing with a vector on the left hand side, and this gamma is multiplying vectors on the right hand side. So what does it mean? It means that whenever I have a tensor field, a rank 1-2 tensor field, and I have one connection, I can define another connection that also allows me to do parallel transportation. Now, we want to, so this is not unique. So what do we talk about? This is parallel transport. Then we have connections. So we want to put some extra constraints to find some connections which are more useful. So one condition that we use is that if I anti-symmetrize a connection with respect to the lower indices, so if I define this as gamma mu alpha beta minus gamma mu beta alpha, this can also be seen as a tensor, and it's called a torsion tensor. So this is torsion. And it is usually set to 0. So this is one restriction. Just to make it more minimal, we can make this extra assumption. Now this has some extra features that we will see just in a moment. Okay, so the moment I learn how to parallel transfer the vector, to define a vector at some take a vector and assign to it an analog in a different point, now taking derivatives of vectors becomes possible. But now we can define covariant derivatives. So before we were saying that we cannot take derivatives if I just have a vector field. So imagine we have vector field a mu of x. Before we saw that we cannot simply take the derivative of this vector field in some coordinate system and obtain a tensor. That is not a tensor. And because of a very simple reason, because a mu at taking derivative requires subtracting vectors at two different points, but the vectors at two different points live in two different tangent space. So that is not that's not a very well defined thing. It's very coordinate dependent how we do it. It's exactly like defining parallel transportation in a given coordinate system. Of course, it always remembers about that coordinate system, which it is different. So this was not good, but now we can use our parallel transportation to define a covariant derivative, which does introduce a tensor field. So instead of instead of subtracting a mu at x plus dx, instead of subtracting a mu at x, we subtract what we call here a tilde. So it's the parallel transported version. And this quantity is now guaranteed to be a well-defined well-defined vector in the new tangent space. So if I subtract these two, I get something that I can call it del mu a mu times dx mu. So this is true for all dx nu, so I can just drop dx nu and define the covariant derivative to be d mu a mu plus gamma mu nu alpha a r. Now imagine I have a curve. I can do this parallel transportation of vector along a curve. So here I talked about an infinitesimal transformation. In principle, we could consider these 2 points P and Q which are far from each other and consider a curve that runs from P to Q. And then we could ask what would be the, we could ask what would be this V tilde. If I have a V inserted at point P, we could ask what is V tilde at point Q. And of course that in principle, in general, that would depend on the curve that I use to do this parallel transportation. So the curve, as we saw the other day, it's a set of points which is parameterized by a number, a real number, and to it we can associate a tangent vector, some T mu. So if I have this rule of parallel transportations and I have a curve, I can ask what would be the vector at a new point, and I can relate it to the I can relate the parallel transportation of vector along a curve to this covariant derivative. So if I have a curve with tangent T mu, which is defined as, so curve is a set of points which is parameterized by a real number lambda, and we define the tangent to the curve as dx mu d lambda. Now if I want to parallel transport a vector v mu along the curve, that would define a set of vectors along the whole curve. So at every point there will be a v mu. So I will have a v that gives me some v with tilde mu of lambda along the curve. And what is the condition? What is the definition of v tilde mu lambda? That's exactly following this infinitesimal rule. So that gives me a differential equation. Every infinitesimal step along the rule, along the curve, is given by dx mu is going to be d lambda times t mu at any lambda. So if I want to go one little step, and the definition for this v tilde of mu along the curve would be to set the covariant derivative of this v tilde mu equal to 0. So if I follow this rule along the curve, this covariant derivative projected along t mu will be exactly 0, because this is exactly this. So when we define the covariant derivative, we exactly use our connection coefficient. In a parallel transportation, we are using this to define the new vector at the new point. So if this dx mu is if it is the displacement along our curve, which is t alpha times d lambda, then by definition that would be correct. So if I take a vector and parallel transport it, then that would satisfy this equation by construction. Now we can also define a curve that has the following property: a curve a curve such that its tangent is parallel transported along itself. Sorry? Yes. So we can consider a curve with the following property. And well, for the moment, I haven't picked a particular connection, but if we take this connection to be something special, then it will be related to the geodesics that we define. So let's talk about these particular connections which are called metric compatible. Imagine I want to do, so we said that we have imagine we have metric on the manifold, so we can calculate lengths, or we can calculate the inner products between different vectors. Now we can put an extra requirements on this parallel transportation, which is that we can require that on the parallel transportation the norms of the vectors remain the same. So if I have two vectors and I parallel transport them along any curve, I want to get the same number for the inner product. So for instance, if I do T mu del mu of G alpha beta times two vectors, say B alpha double beta, I want this to be 0. What does it mean? It means that as I parallel transport these two vectors, I want to get the same inner product of these two vectors. And if I require this to hold for all vectors, all VW and all curves, that implies that the covariant derivative of G alpha beta has to be 0. Because if I act by covariant derivative on V or on W, just by definition that I am parallel transporting them, those terms are going to be 0. So that was just a definition of parallel transport. But that implies that for this inner product to remain constant along the curve, that condition should be satisfied. If I wanted to hold for all t's, all t mu, all v mu's, and all w mu. Alright, so this is an extra condition on our connection. So we first require that the torsion is 0. By the way, if the torsion is 0, that implies something about this covariant derivative. So the fact that torsion is 0 implies that torsion freedom implies that if I take d nu of some scalar, any scalar quantity, that is equal to d mu del mu of it, as one can explicitly check. And okay, so if I impose this extra condition, then it uniquely fixes or connections to be the ones that we already defined before, the Christoffel symbols. And then if I look at this equation, equation for a curve that is being parallel transported along itself, then that equation is going to look like the geodesic equation that we were deriving by extremizing the length of a curve. So that equation in this notation is going to look like d by d lambda t mu is equal to minus gamma this equation, if I use, this is true in general, but if I use this expression for gammas, then it will look exactly like the equation that we had for the geodesic. If you also remember that this t is nothing but dx by d lambda. You just need to rename lambda by tau. Now this parallel transportation might sound a little bit abstract, or this is stuff that I introduced here, but in reality it's something very simple and trivial. We all know it by heart. What does it mean? Especially in the case when we talk about the metric compatible connection. So imagine we live on the surface of the Earth, which is a curved surface. It's something like a ball or a potato. And we don't have any difficulty parallel transporting vectors on the surface of the Earth. The only thing that we need to do is that we know that locally we can choose flat coordinates, locally Euclidean coordinate system on the Earth. So at any point, I can choose a coordinate system that around that point looks like flat coordinates, in the sense that so let's choose this point P. So we can choose coordinate system so that g mu nu at point P, let's say we are Euclidean, we just delta mu nu, and then also the derivatives of g mu nu at point P are equal to 0. So what does it mean? We are choosing a locally inertial frame in a sense. Or now if we are in If you are talking about Euclidean geometry, then it's just a local Euclidean coordinates, local Cartesian coordinate system.
I have a question.
Yeah.
Why do you demand the derivative to be 0? Do you demand it to be the maxima or the minima or something like this of the matrix?
Yes.
Because it's just a point, right?
I'm saying that I can choose a coordinate system so that in its vicinity,
Yes.
it looks like a flat coordinate, a patch of flat space. If I have non-zero derivatives, then it won't look like a patch of flat space because it will have a preferred direction.
Okay, so it's locally flat, right?
Yeah.
In a region.
But it's not. It's actually not. The higher derivatives of G are non-zero.
Yes.
But those introduce some scale at which you deviate from flatness.
Yes.
So as you go away, there will be deviations from flatness. They start from the second derivative, which are order x squared. So that I cannot do anything about. But the best that I can do is to choose these local inertial frames for which g and the derivative are 0. So what happens when the g and the derivative are 0 is that the gammas will be 0.
Yes.
Now in this coordinate system, we know exactly how to do parallel transportation because we do it the same way that we do it in Cartesian coordinates. So on this blackboard, there is no ambiguity in transporting this vector from here to the other side of the blackboard. Since it is flat, we just identify the components of the vector. So we do the same on the surface of this curve. On this curved surface, we choose a locally flat coordinate system, and so suppose I have a curve here and I have a vector. In this locally flat coordinate system, I just move my vector following the routes that I know from Euclidean flat geometry. And then at the new point, I choose another coordinate system which is inertial at that new point, and I continue. So for instance, imagine I'm on a sphere on the equator. Say I have a vector that points towards north. Then I can try to parallel transport this vector to the north pole along the longitude phi equals 0. So this is phi equal to 0 longitude, and this is my vector. Again, there's no ambiguity how to parallel transport it. We just do little steps. At each step, I know how to move it parallel to itself in that small region because I choose the locally flat coordinates. So as I arrive in the north pole, it will be this vector. Then I can bring it back to the equator along the line longitude phi equals pi over 2. It's going to now be parallel to the equator.
Why is it radial now? In the radial direction?
No, it's not radial. It's now now it points along, so here it would point along minus theta hat.
Yes.
Now it points along phi hat because I took it to the north along the phi equal to 0 longitude, but now I'm bringing it back along the phi equals pi over 2 longitude.
Yes.
So now it's going to point along phi hat. So as I arrive, it points like this, and then I can go back to the original point. And I end up with this vector. So I started from a vector that pointed towards north, and I ended up with a vector that points along east. So I got a rotation of pi over 2 by doing this parallel transportation. At every infinitesimal step, there was nothing surprising happening. But once you do a big, go along a big loop doing this parallel transportation, you get a vector that doesn't agree with the original one. Or in other words, parallel transportation along different paths does not have to give the same result. It's going to give a vector, but not the same vector. It is a path dependence. The path dependent procedure. It wouldn't be path dependent if the manifold was flat. But if there was it was just a single coordinate system, flat coordinate system that covered the whole manifold, then it wouldn't matter if we do it step by step or we do the whole thing in one step, because the whole thing would be done in one Euclidean patch. While here, in order to do it, you have to do it in several steps and use different coordinates that do not cover the whole manifold or are not flat in the whole manifold. So parallel transportation is path dependent, and it is a measure of the path dependence of parallel transportation is a measure of how deviation from flatness of the manifold. So this can be formalized using the Riemann curvature tensor. So the analog of this path dependence, if I want to do it infinitesimally, is that if I do go along two different directions, or go along a loop, or go from point 1 to point 2 in two different orders. I first do dx1, dx2, or I first do dx2 and then dx1. And the result of this parallel transportation depends on which order I use. So that is equivalent to saying that as we saw, the parallel transportation is what we use to define the covariant derivative. So the mismatch of this parallel transportation is related to the commutator of covariant derivative. As you see, in order to do parallel transportation, we set this equation to 0. So the mismatch of these two procedures, if I apply it to a vector, lambda, that is equal to minus Riemann curvature tensor alpha lambda beyond. And this is the definition of the Riemann curvature tensor. questions so far? Yeah.
Is there another geometric interpretation for the torsion construct?
Probably there is, because it's called torsion, but I don't know. Wait, it is related to non-commutation of derivatives on a scalar field. So one would think that it should be something like, if I want to act by the commutator on a scalar field, then I will get torsion, right? But we are not part of transporting the scalar field, so that I don't know. Geometry. Yes.
Torsion free means that the derivatives commute. Torsion free means that the derivatives commute. The covariant derivatives commute.
When I act on a scalar.
Okay.
Because the definition of the covariant derivative depends on what type of tensor they act on.
In the case of a scalar field, there is no connection.
No, the covariant derivative of a scalar is just the mu of it. But then you act with another one on del mu of f, and now this is a covector. So there will be a connection involved in here. But that expression gives me exactly the torsion times the derivative of the derivative of the scalar. So this is d mu f minus gamma mu alpha d alpha of f. And then if you look at that commutator, this minus that equal to 0, this is equal to gamma mu alpha minus gamma mu alpha times d alpha of f is equal to 0 for every act.
One question. This procedure of creating connections. I mean, it seems very similar to like when we have gauge symmetries and we want to make like a covariant derivative as well, and we introduce like something. And also to get the curvature in the case of spin 1 massless, we also get the f mu nu, the tensor, by taking the commutator.
Right.
There is something. This is there is like a reason because all of these things are similar. I don't know, because we are doing the same. I don't know.
Yes. So if you look at it from the particle physics, from field theory point of view, as we were doing before the last lecture, they are almost the same thing. You have a U1 gauge symmetry for the spin 1 massless spin 1 field, and here you have the diffeomorphisms. for the massless spin 2 field. And then the covariant derivative is the exact analog of the covariant derivative in the U1 case. There you have this field A mu, which acted like connection. Now here you have metric out of which you construct the Christopher symbol that acts like connection. So from that perspective, they are identical. It's just a different gauge symmetry, different gauge group. From a geometric point of view, you need to come up with a geometric picture of the U1 connection, which also exists. I haven't talked about that either, but yes, you can also give a geometric picture to that, and then it becomes similar.
Then
Now you want to define quantities at different points, but you are, when you have U1 gauge symmetry, then you have some object, some observables which are charged. But then you, since you have gauge symmetry, you can do gauge transformation, which are U1 transformations which are independent at different points. So if you want to compare two quantities at two different space-time points, you need a connection. And the connection has the property that it transforms according to the transformation laws. So you can have nodes and you can have links. And then you have independent U1s at every point. So let's give them index U1, 1, U1, 2, U1, 3, and so on. So then you can have charged fields that live on these nodes, psi 1, psi 2, psi 3, and then you will have connections that live on the links. And connections allow you to subtract, define derivatives, to compare fields that different at compare fields that live at different points. So it has the same, it can be given the same interpretation. Yeah.
Well, in the case of one other step that we do in electromagnetics, for example, is create a connection that in the case of U1 is an spin one particle A mu. Here, the connection can be also like an extra gauge group, an extra field or something.
But here is connection is gamma, but it is constructed out of the metric, and the metric, if you remember, at least when we are close to Minkowski, the metric is eta min. Well, this I can always write, but as it comes to Minkowski, you can think of it as just a two-index field.
There are also derivatives on the metric that make it very super high nonlinear.
Not nonlinear. You can linearize it all. It is nonlinear, but you can linearize.
Okay.
Yeah, I guess if you want to write the exact covariant derivative as we are doing now, it is very nonlinear in H. That's true.
Okay.
Okay. So Riemann is telling us how parallel transportation is path dependent, or how covariant derivatives do not commute with each other. So let us understand what are the symmetries of the Riemann. First of all, it's defined as the commutator of two covariant derivatives, so it has to be antisymmetric under the exchange of first two indices. Secondly, we said that the power transportation that we are using, which is metric compatible, is it preserves the norms. So this extra indices that act on these two indices that act on V, they should act like, if we are in Euclidean geometry, they should act just like a rotation. They shouldn't change the norm, but just rotate the vector. If we are in Lorentzian, then they can be either a rotation or a boost. So what does it mean? If I lower that index by a metric, then this has to be like a generator of a rotation or a boost, and we know that it is the generators of rotations or boosts are anti-symmetric. And then there is this last property that is related to the fact that the exact forms are closed. So if the omega, well, I haven't typed out forms, so you can just accept it or see it from the definition. So from this definition, of course, I can derive R, the explicit expression for R. And then from the explicit expression, one can see that there is another symmetry. It's related to the fact that the exact forms are closed. That implies that R mu nu alpha anti-symmetrized is equal to 0. And that implies that if I combine it with these two other symmetries, that implies that if I exchange this pair with that pair, I get the same. So it is symmetric under the exchange of the first pair and last pair. So let us work out one explicit example. Let's derive Riemann for a sphere. So I want to derive R mu nu alpha beta for a 2 sphere. So how do we do that? Say it again.
We need to define a metric.
We know that metric on the sphere. So for S2, for instance, we know that there is we can use theta phi coordinates. And the metric is going to be d theta squared plus sine squared theta d phi squared. And then given this definition for Riemann, of course we can derive the explicit expression for Riemann in terms of the metric. So that tells us that if I lower this and raise that, then there will be some some expression for the Riemann in terms of the connection, Christoffel symbols and its derivatives. So d alpha gamma mu beta minus d beta gamma mu alpha plus gamma mu alpha lambda gamma mu beta lambda so it has some expression in terms of metric and its derivative. The only thing that is important in this expression is the fact that there are two derivatives. There is one inside gamma and then one here, or here we have two gammas, so there are in total two derivatives. Given the metric, of course, I can plug it in here and calculate it. It's usually a bit painful to calculate Riemann. There are many indices. But there are special situations in which you have symmetries and many of the components of Riemanns are actually zero. Moreover, symmetries allows us to do things, use simple tricks to do calculations. So that's why I'm talking about this too, because I don't need to do this computation. I can just use symmetries to almost fix Riemann up to a single number. How do we do that? First of all, we notice that all points on a sphere are equivalent to each other. So in a sense, it is maximally symmetric. There is no special point on a sphere. Every 2 points are the same. So let's take one single point and bring the metric into this form, this diagonal form. So for instance, in this theta phi coordinate, if I want the metric to look like a diagonal metric of Euclidean space, I should go to the points on the equator. On the equator, these theta phi coordinates are like the usual flat coordinates. At other points, they are not. So let's go to the point at which the metric is just diagonal. And ask how would Riemann look like at that point. So now let's use the symmetries. Based on the symmetries of the Riemann, it's a two-dimensional space, so we don't have too many indices. It's just 1 and 2. And the only non-zero component of Riemann is going to be R1, 2, 1, 2. And the ones that are related by these two, by symmetries, because it's anti-symmetric with respect to these two. So if one is 1, the other one has to be 2, and similarly here. So that's this one, and everything that is related to this by those symmetries are the only non-zero component, and they are all the same. Because they are connected by symmetry. Now I can write an expression for Riemann in terms of the metric. Where this C is okay. So first of all, I'm claiming that this is the general form of the Riemann tensor with some constant C, and So why is it true? It's true because if I go to this coordinate system, one can check that this expression on the right hand side has the same has the same property as Riemann. So it has, this is, well, even without going to that coordinates, this has the same symmetry. This anti-symmetric under the exchange of mu and nu, anti-symmetric under the exchange of alpha and beta, and then it's symmetric under the exchange of the pair. So it has the right symmetries as Riemann. Now if I consider some 1,2 component of this in this coordinate system, then the right hand side is going to be, so R1212 is C times, so I have mu is 1 and nu is 2 and alpha is 1, beta is 2. So I have G11, G22 minus G12, G12 or G21. So in that particular coordinate system, this guy is G bar.
Well, you see.
This is just C times G11, G22, which is just C, because G11 and G22 are 1. So in that coordinate system, that C is given by R1212. So if I fix Riemann R1212 in that coordinate system, in which metric is diagonal, I fix C, and then I know Riemann at every point on the sphere in any coordinate system. So the only thing that I need to do is to determine this non-trivial component of Riemann at one point. Now how is it defined? It's defined, this R1212 is defined by the following. If I go along a little square, if I parallel transport along a little square, I get a small infinitesimal rotation, which is proportional to the area of this square. Right, it's proportional to x1 and x2. So I just need to find the, and this is a rotation. Well, we only have 1,2 plane, so this is a rotation in 1,2 plane, which is proportional to the area of this square. So I only need to define what is the rotation that I get per unit area when I do this parallel transportation. That determines R1212. However, since the sphere is maximally symmetric, I get the same rotation also doing parallel transportation here around this square, and the same here. So I can draw these little squares and tile the whole region that we talked about before with these little squares, and ask what is the total rotation that I get. I add all these little infinitesimal rotations that I get along these different squares. Every one of them is proportional to the area of this square. So as I send the area to 0, it goes to 0. So if I add them up, I will get the total rotation that I got by doing parallel transport along this big loop. The total rotation that I got was pi over 2, if you remember. So the total delta theta was pi over 2, and the area, so this is just 1/8 of the total area of a sphere, which is 4 pi. This is a unit sphere. So this is also pi over 2. So that tells us that the angle per unit area is just 1. So R1212 is just 1. And that fixes C to be 1.
That means that the curvature. What does it mean in terms of curvature? That we have that is just a constant. That is like the same curvature everywhere, something like that.
Well, the curvature is a tensor. And the tensor is given by this expression. I just did that to fix the constant here. So this constant is 1. So you could try to calculate some scalar quantity out of this, like a square this one, calculate the norm of this, or contract it by itself, and then you will get a single number, which is, you will get a scalar, and then that scalar has some value at different points. In fact, it has the same value everywhere, and that is exactly what we mean when we say that it's maximally symmetric. No 2 points on the sphere are different. Every 2 points are identical. If it wasn't the case, it would mean that you can go and measure something and distinguish between 2 different points on a sphere, but that's not, that's by definition not the case. So coordinate systems can differentiate between different points on the sphere, but any quantity that corresponds to the experience of those little creatures that live on the sphere cannot distinguish between different. That's what it means. Any questions? Okay, so we can finally come back to the Einstein-Hilbert action for general relativity. This will come back to physics. If we try to say that, as we saw before, if we say that we want to construct a theory and action, a gravitational action for the metric, if we say that metric is our degree of freedom, then we can, okay, so maybe before that I should say something. So of course this is the goal. We saw that we are talking about the spin 2 field, and in order to construct a consistent theory for a spin 2 field, we have to put it inside a metric. And you have to construct a theory which is diffeomorphism invariant and is made of this full combination, eta mu nu plus g mu nu, which we call it the metric. So then we found the rules for constructing the matter action. If the next question was about what would be the gravitational action that a linear order agrees with or linearized theory or quadratic action that we derive for h mu nu, and at higher orders it satisfies the rules that we have, which was diffeomorphism in value. Now we have discussed manifolds, we have discussed curvature, we have talked about manifolds which have a metric leaf on them, and we said that we can define this curvature, which is a measure of, we can define this Riemann tensor, which is a measure of how curved the manifold is. And it's something that is constructed out of metric, two derivatives of the metric, different metric components. One other piece of information that I forgot to say, which is very important, is that the knowledge of Riemann and its derivatives allows us to reconstruct the metric at any given point up to Lorentz transformation. So that I'm not going to prove. But the statement is that the metric can be fully reconstructed so given Riemann and its derivatives, all derivatives of Riemann, we can reconstruct the metric at a given point. So if I know that all derivatives of Riemann at point P or at point x mu, then I can reconstruct the metric in the vicinity of that point up to the freedom of doing some Lorentz transformation. So this can be done constructively. One can construct this, the so-called Gauss normal coordinates, or Fermi normal coordinates. So that what they do is that it's exactly this. Given the curvature and its derivatives, they construct the full metric in the vicinity of the point. So all of the information about the metric or about the manifold is captured in Riemann and its derivative. So therefore, this action that we want to construct, if it is something that wants to, we usually define action using the integral of some local quantity. So this action should also be constructed out of Riemann and its curvature and its derivatives. Sorry, let me get some water. Yes, So the rule was that we want to write it as an integral, a volume integral. And that was our integration measure. This Lagrangian should be constructed out of Riemann and its derivatives. So what are the options? One option is that you take L to be 1 or a constant. That is called the cosmological constant. It can be put there. There's nothing wrong with it, except that if we want to construct a theory along for Minkowski spacetime, that has to be 0. So that if I have non-zero lambda, that means that my spacetime is not Minkowski, or my vacuum is not Minkowski. It is going, depending on the sign of lambda, it's going to be de Sitter or anti-de Sitter. In fact, the right choice for the universe we live in is that lambda has to be positive and non-zero. So this is called cosmological constant.
I have heard that the measure said that it is not like a flat space.
Right.
I have heard that the people were like measuring the curvature of the universe, and they think that it's very close to 1 or very close to flat space. It's not that we need flat space.
Well, I'm not sure what exactly you have heard. So you might have heard about the spatial curvature of, like if you heard, maybe if you remember Alan Goose's talk, he was talking about the spatial curvature. That's a different thing. So in FRW cosmology, you will see it later. You can talk about the spatial curvature of constant time slice. So essentially the idea is that if you have some choice of time slice, you can ask about, so let me give you the example on the speed. So you have some your preferred coordinate system, let's say this theta and phi coordinate, and lines of constant thetas are latitudes, right? Now these latitudes are not geodesics, except the one on the equator, right? These ones are not geodesic. When they are not geodesic, it means that they have some acceleration. If you think of it as in our example of a point particle, this is just Euclidean version of the same thing. If it's not geodesic, it means that on the right hand side of geodesic equation, instead of 0, you have something else. You can call it the acceleration. Now, go to higher dimensions and to a space-time, then, so this was constant theta lines, which have non-zero acceleration. So you go to a space-time, 3 plus 1 dimension, and look at the constant time slices. In particular in cosmology, look at constant time slices. Those constant time slices, you can ask what is the curvature of those surfaces. And that is called a spatial curvature. That is very close to flat in our universe, yes. What this tells you is the curvature of the whole space-time. So this is some, here for instance, the non-flatness or deviation from geodesic of these lines has something to do with your choice of coordinate system. You would pick constant theta lines, and then that would tell you that whether this line is a geodesic or not. the fact that the sphere itself is curved, it has some curvature, that's an intrinsic property of the sphere. It has nothing to do with your choice of coordinate. But the fact that there is that non-zero component of Riemann, when I go to this special diagonal metric, that is some intrinsic property of this space-time. In particular, you can calculate some scalar quantity by contracting different components of Riemann. So there is something called Ricci tensor, which is obtained by contracting these two indices of Riemann. And from this we can also calculate Ricci scalar, which is obtained by doing this extra contraction. So for a sphere you can calculate that and you get some non-zero number, some positive number. It's very easy to calculate given that expression. So that is a very intrinsic property of this sphere compared to this curvature of these lines, which is not intrinsic. It's up to your. It depends on the choice of the line that you consider. So the statement is that if lambda is in our universe, we have positive lambda. So it's a Lorentzian analog of a forest sphere. Okay, the next choice would be, again, we said that this has to be a scalar, so the next choice is the Einstein-Hilbert action with some constant, which using a comparison with Newtonian limit, we fixed it to be, what was it, 1 over 32 pi g, something like that.
Mm-hmm. 16.
16. Of course, if we want to allow higher derivatives, we can go further. We can consider Riemann squared, we can consider derivatives of Riemann. But as I mentioned a few lectures ago, the higher that we go in the number of derivatives, the less important become those terms as we talk about larger scale physics, long distance physics. So those terms are in principle there, but as long as we care about the low energy physics, they are phenomenologically irrelevant. Okay, so that was today's lecture. Actually, everything that I'm supposed to tell you.
So when is our exam and what will we do on Friday?
On Friday we can continue with the rest of problems.
Yes.
Yeah, maybe we can meet a bit earlier, like at 1:30. Because there is a talk at 2:30 that I want to go. So we can continue on problems. If there is time, then I may solve one of the problems of this suggested problems at the very end of the lecture notes. Next week there is one tutorial on Tuesday. It won't be by me, maybe Paolo will do it. And then there will be a midterm on Friday during the class.
Where do we study from for the midterm? Again, when there's like sources of problems, or what should we do?
I would say the homework. that's the best setup.
Exam is going to be as difficult as home.
No, I try to make them easier. Also, there are some problems in the homework which are not very central. So there are some more central topics which are more important. And then there are others which are more for fun or for extra additional information. So if you want to prepare for the exam, make sure that you understand the more basic central topics, which if it's not obvious, I can just list them right now for you. There is, basically, I would say there are 3 important topics that you should be very well prepared in. So one is redshift. Second is geodesic motion, especially in the fields with high amount of symmetry, and then obviously gravitational waves. So if you have learned these 3 things, you have accomplished what I expected you to do from the first part of the course. Okay, maybe I should put also the conservation laws here. Or a stress energy tensor. Conservation laws. Okay, so Friday, let's meet at 1:30.
How many hours is going to be the exam? How many hours is going to be the exam?
It will be during the class time, 1.5 hours.
Okay.
See if this process calculate spinning objects. Calculation of spinning objects.